Hello, I'm Haozhi Zhang from Weilin Technologies. I'm going to present our work, Cross-Batch Memory for Embedding Learning. Mining informative negative instances are of central importance to deep metric learning, but it is limited by mini-batch training, where only a mini-batch of instances is accessible at each iteration. It lacks this figure. It is difficult to put a big elephant into a small box. How to collect informative samples from the whole dataset? There are two groups of approaches to improve such ability for deep metric learning. The first one is to weight the pairs of current mini-batch, such as lifted structure loss and melted similarity loss. The second group of methods focus on sampling more meaningful mini-batch, such as divide and conquer in CVPR 19. However, both approaches are inherently limited by mini-batch training, where only a small piece of instances is accessible at each iteration. A straightforward solution is to enlarge the batch size. We study the performance of three widely used loss functions with increasing batch size on three large-scale few-shot datasets. We observe that the performance consistently grows with the increasing batch size. However, batch size is limited by GPU memory and cannot increase arbitrarily. To collect a rich set of hard-negative pairs, we are inspired to break the limitation of mining informative pairs from a single mini-batch. Intuitively, the features at past iterations are out of date because they are generated by the past models, which is less optimized than the current one. But how much difference between the past features and the current one? To measure such difference, we define feature drift, which measures the feature distance of an example at iteration t and iteration t minus delta t. As shown in this figure, we can find that except the first several hundred steps, the feature drift actually very slow even under a large interval of 1,000 steps. This inspires us to explore the features computed at the past training iterations and enables us to access the whole training set using such past features. We propose cross-batch memory to catch the features computed in the past iterations. Here is our framework. We train an embedding network by using pair-based loss functions in terms of pairs between current mini-batch and the memory bank. At each iteration, we increase the embeddings and labels of the current mini-batch and decrease the entities of the earliest mini-batch. So our memory module is updated with the embeddings of current mini-batch directly without any additional computation. Our cross-batch memory is easy to implement by just using several lines of code as shown here. As shown in this equation, to calculate the memory-augmented pair-based loss, we simply compute a cross-memory similarity matrix S between the instance of current mini-batch and the memory bank. This allows us to collect hard negatives over the whole memory bank, which is possible to cover the whole training set. For example, when we train a pair-based loss with a batch size of 64, we only can collect the hard negatives pairs from a small 64 times 64 pairs. But with the memory bank, we can easily enlarge the search space to 64 times 60,000 pairs, which are about 1,000 times larger. We first verify by experiment on how many negatives can be found with and without memory. As shown in this figure, with a memory module, we can collect over 100 times more hard negatives than the single mini-batch. We compare negative images found from a single mini-batch and those found from our memory, as shown on the top and bottom. The single mini-batch can only find a small number of negative samples which are dissimilar with the anchor image, while our memory is able to collect a rich set of hard negatives which are visually similar with the anchor, for example, different types of bicycle. We evaluate the performance of our cross-batch memory on SOP dataset. We found that the performance of cross-batch memory with a 16 mini-batch size is comparable with the performance of 256 mini-batch size. And our method requires a significantly less memory and training time than the large mini-batch training. For example, cross-batch memory only needs 0.2 GB additional memory. More experimental results show that cross-batch memory can consistently improve the performance of various loss functions and different datasets by a large margin. We conduct extensive experiments on three image retrieval benchmarks. With cross-batch memory, a simple contrastive loss easily surpasses the state-of-the-art methods by a large margin. We believe our work can provide a new path in solving for hard negative mining, which is a fundamental problem for various computer vision tasks. The identified slow drift is a general phenomenon not only occurring in deep metric learning. We hope it can be extended to improve a wide variety of machine learning tasks. Code will be released in our website. Thank you for your attention.